Welcome to Dr. Jimmy's Applied Calculus. Ready for section 4.2. I'm going to look at the definition of some creature called a derivative. So let's recall a little. If we have a curve, I'm looking at a value x sub 0 here. We add a change in x called h. So I made delta x in this, relabel that as h, a little less cumbersome notation. So change in x will be h. For each of those values, we have a point on our curve. So if our curve is given as y equal f of x, we have the one point at x0, the height will be f at x0. We add a change in h, end up at x0 plus h. The new height will be computed as f of the value of x, which at that point is x0 plus h. So if we take a secant between the 2 points, we get a straight line. And so we have this hypotenuse of a triangle that has change in y over the change in x. So change in y over the change in x. We have change in y over, I've relabeled change in x as h. What about the change in y? Well, that's the change in the coordinates f of x0 up to f at x0 plus h. That would be changes in f are the changes in y. So the difference in the values of y. So the slope of that secant line between the 2 points is given by this change in f over change in x. Now, if we take a direction or slope at the point above x sub 0, this secant line slope is an approximation to the tangential direction slope. So in this picture, maybe not such a good approximation, but the idea is to move the point by making h smaller, and then we end up closer and the secant line is a better approximation in its slope to the tangential direction. So we came up with this setting. That the tangential slope or direction on the curve instantaneously is a matter of making the change in x smaller and smaller, a better approximation. And now we have a way to look at, well, how small? Well, as small as we want by taking the limit as h approaches 0. So we have these changes in y over the changes in x as slope approximation. Take the limit as h to 0. We should get the slope of a general curve at a point. Now, this sort of analysis of changes has a much more general setting than just a geometric picture. So we have a general terminology for this limit. So in general, this limit we were looking at is called the derivative, and then referencing of f, or we could write out y equal f of x at a particular value. So what we're doing is computing old familiar line slopes and then taking a limit. In general, this creature is called the derivative. So little pieces of information at a particular instance. What is happening? What's the direction? Is things getting better or things getting worse? That type of situation. So, being very little pieces of what's going on, maybe the word derivative makes some sense for that concept. Now, the derivative over time has been given some notation. So instead of writing out this limit each time, there's one notation that the derivative of f at x0, so if we reference f and the value x sub 0, we would just need another piece to tell us this is the derivative and not the function. And so one way is a prime symbol. So f prime of x0 sometimes is the way it's phrased, represents this limit, which is the derivative of f at x0. Over time, another independent notation was developed. And so it's the limit of these changes in f or y divided by changes in x. So that notation, if we change the deltas to d's, that represents the derivative of f. And so again, we get the derivative of f at x0. So two basic notations we might use. And it's convenient over time that we have two different ways of labeling the same thing, because characteristics of the notation lend themselves well in different settings. So, derivative, as far as a picture of the graph, represents that direction or slope at a time. In general, it's going to look at how things change. Okay. The relative change, a change in f in ratio to a change in x. How do things change, but in a relative fashion? Not just a change, but a change divided by a change. What's the ratio of change? So let's look at some example situations here. In all of these examples, we'll take y equal an f of x, which is 2x squared minus 5x plus 6. We'll use that as our example curve. And so, first thing we'll do is find the derivative of f, and I'll use the prime notation here, at a value, say we'll use 2. So, pictorially on that curve, what's the direction or the slope at the value 2? So, we're going to have to look at this limit. H is approaching 0 of 2 plus h relative to 2. So we'll have start at 2, add h, compute f at 2, compute at 2 plus h, and take the difference. So for that purpose, let's separate out a few things. Let's find the value at 2. So 2 times 2x squared minus 5 times 2 plus 6. So we come out with a value of 4. Now in our limit, we also need what is f evaluated at 2 plus h. So 2, and then we square 2 plus h, minus 5, and then the x becomes 2 plus h plus 6. So, expanding and collecting like terms, we will take 2 plus h. This square is actually, we'll end up with 3 terms. So we get 2 times 2. We get h times h, but we also have the multiplications 2 times h and h times 2. So another 4h. A power of 2 terms will give us several terms in the answer, not just 2. And now we can distribute minus 5 times 2, minus 5 times h, and we still have the plus 6. And finally here I'll multiply and distribute the 2, getting 8 plus 8h plus 2h squared, and then the rest of these terms, minus 10, minus 5h plus 6. And so, combining like terms, 2h squared, we have 3h and then we have plus 4. So, if we take f at 2 plus h, which we just wrote here, and subtract f of 2, let's take the quantity 2h squared plus 3h plus 4 and subtract 4, ending up at 2h squared plus 3h. So going back to the limit, numerator being this difference turned out to be 2h squared plus 3h, and the denominator is still h. Progressing here, we can divide h into each term. So 2h squared divided by h is 2h. 3h divided by h would be 3. At that point, when we do limit, we can substitute, end up with 2 times 0 plus 3. So we get a slope, or a derivative of 3 at 2. Now, what we just proceeded through, we could attempt to do in general. So instead of picking a particular value for x, we'll do it at each x and see if we can simplify the limit in that case, in all cases at once. So that would be looking at the limit, change in f. So start at an x, add an h. So instead of just a fixed 2, we'll use a symbol x and then divide by h. So we need to work out this limit. So again, let's do this in pieces and then bring it back and substitute into the limit. So we'll recall f of x was 2x squared minus 5x plus 7. Actually plus 6. So that's where we started. We also need f evaluated at x plus h. So we would have 2, we would have x replaced by x plus h, so x plus h quantity squared minus 5, another x which is replaced by x plus h plus 6. So I'm going to expand and collect like terms again. Remembering that if I square this 2-term expression, I will get x squared and h squared, but I also get the multiplications x times h and h times x. So I'll end up with 3 terms from that multiplication. And then continue minus 5 times x and minus 5 times h. Still with the plus 6, and then 2 times x squared, 2 times 2xh, and 2 times h squared. Now, if I attempt to collect like terms, there are no like terms. So I'm, at this point, ended that. Now what do I have to do? I have to look at this last expression that I came up with for f of x plus h and subtract f of x. So if I'm subtracting 2x squared, that would be this term. So 2x squared minus 2x squared. I would subtract the minus 5x squared from this expression. And also subtract the 6. So that would leave just 4xh plus 2h squared minus 5h. So this f prime of x, or the derivative of f at x, should be the limit as h approaches 0 of f of x plus h minus f of x divided by h. And now we've found that the numerator in the expression would be 4xh plus 2h minus 5h that we have up here, all divided by h. And so I'll take this step of dividing each term by h. So I have to divide each term, not just one. And end up with 4x plus 2 minus let's copy correctly before I get further. I believe I should have had 2h squared there. So that leaves an h minus 5. And so if I take h going to 0, it does not affect 4x. There's no h. 2h becomes 0, and then minus 5 unaffected. So I end up with 4x minus 5. So now that I have a general form of the derivative, I could have used this to find the derivative evaluated at 2 and came up with the same value of 3. So it depends on the information we might have when we deal with this derivative, the related change in a situation. In some real problems, we have only data sets, so it's only we can approximate using these approximate changes with the idea of moving the h as much as we can to get better approximations. In that case, just numbers. In other cases, we know the model and we know how it changes, so we're going to have things more related to an expression for the derivative that we can substitute and find values. And so we can begin to ask questions about what's going on once we know how to find a derivative. such as what's the tangent line to this curve y equal f of x at x equal 2. So there's a point of tangency. So at what point are we looking and taking our direction? So that would be x is 2, and so the height up to the curve is the f of 2. And so I think we already found f of 2 before to be 4. And then there's the slope. And so the instantaneous slope at the point, or the tangential direction slope, is this creature we now call the derivative evaluated at 2. And so we found that value to be 3. And so we get a tangent line would be y minus the y coordinate of the point on the line is equal to slope x minus the x coordinate of the point. So there's one form of the line. We could write it y equal 3x minus 2 is the same line, if you prefer that slope-intercept form.